Hey everyone, welcome. So, have you ever wondered why a metal spoon gets hot like instantly in your tea, but the mug itself takes ages to warm up? Or, get this, how do fish stay alive when a lake freezes over? Well, the answer to both of those is heat. And today, we're going to tear down this entire grade 10 chapter piece by piece to make sure you absolutely crush your exam. Ready? Let's get into it.
Okay, so here's our roadmap. First, we'll nail down what heat energy even is. Then we'll look at how we measure it, the 3 ways it gets around, and a really surprising trick water can do. After that, we'll uncover a material's secret power, and then tie it all back to your everyday life. Let's jump right into the first part.
All right, first up, what is heat energy? Look, before we can get to all the cool applications and tricky problems, we've got to build a rock-solid foundation. So when we use the word heat, what do we actually mean? Let's get this crystal clear. So think about it like this. Every single thing around you, your desk, your phone, even the air, is made of tiny particles, right? Atoms and molecules. And they're not just sitting still, they are constantly jiggling and vibrating and zipping around. Thermal energy is just the total energy of all of that chaotic random motion added up. It's also called internal energy, basically everything going on inside. Okay, now this next part is maybe the most important concept in the whole chapter, so really lock this in. An object doesn't possess heat. That's a common mistake. Heat is the transfer of thermal energy. It's energy on the move. Think of it like a message being sent. It's not the phone, it's the signal traveling between phones. And it always flows from a hotter object to a colder one. Always. So what's the deal with heat versus temperature? This pops up on exams all the time. Here's the key difference. Heat is about the total energy being transferred. It's measured in joules. Temperature, on the other hand, is the average energy of the particles. It's about how fast on average those little guys are jiggling. Here's a mind bender for you. A giant iceberg has way more total thermal energy than a small cup of boiling coffee. But the coffee has a much higher temperature because its particles are, on average, going absolutely wild. All right, time for some important exam questions. Get your notebooks ready? First question, differentiate between thermal energy and heat energy. Your answer should be simple. Thermal energy is the total energy inside a body. Heat is the transfer of that energy. Got it? Okay, second question. What is the SI unit of heat? The answer is the joule, spelled Joule. Don't mix that up. Okay, moving on to temperature and measurement. We've talked about how temperature is this measure of hotness or coldness, but, just saying something is kind of hot isn't going to cut it in physics, right? We need numbers. So how do we actually measure this stuff accurately? Well, we use a thermometer, of course. And how does it work? It's based on a really simple idea. Things expand when they heat up. Most liquids, like the mercury or alcohol you find in old thermometers, take up more space when they get warm and shrink down when they cool. So by putting that liquid in a super narrow tube, even a tiny change in temperature makes the column rise or fall a noticeable amount. Simple, but brilliant. But just having a tube of liquid isn't enough. You need a scale on the side. And to make a scale everyone can agree on, you need fixed points, things that happen at the exact same temperature no matter where you are. The 2 big ones are the melting point of ice and the boiling point of water. As you can see here, Celsius, Fahrenheit, and Kelvin all use these same events but just assign different numbers. You have to, I repeat, have to memorize these values. 0 and 100 for Celsius, 32 and 212 for Fahrenheit, and 273 and 373 for Kelvin. And this right here is the ultimate conversion formula. It's like a master key that unlocks any conversion problem they throw at you. It connects all 3 scales in one go. See how they're all equal? If you need to go from Celsius to Fahrenheit, you just ignore the Kelvin part, plug in the number you know, and solve for the one you don't. This formula is a lifesaver for numericals, so make sure you write it down, big and bold. All right, section 3, how heat travels. We know heat is energy on the move, but how does it actually, move? Turns out there are 3 main ways it gets from point A to point B. Think of them as the 3 highways of energy transfer. This simple image of a campfire is perfect for showing all 3 at once. If you touch the metal poker, the heat travels through it to your hand. That's conduction. The hot air rising above the fire, that's convection. And the warmth you feel on your face just from sitting near it, even through the air, that's radiation. Let's dig into each one. Okay, let's break these down. First up, conduction. This is heat transfer through direct contact. It happens mostly in solids. Imagine the particles are like a line of dominoes. You jiggle the first one, it bumps the next, which bumps the next, and the energy passes all the way down the line. Next, convection. This happens in fluids. That means liquids and gases. Hotter stuff becomes less dense and rises, while the cooler, denser stuff sinks to take its place. It creates this circular flow, like a current. Finally, radiation. This is heat transfer through electromagnetic waves. It's pure energy, and it's the only one that doesn't need a medium. It can travel through the total emptiness of space, which is how we feel the heat from the sun.
Okay, let's talk about some of heat's surprising effects. Normally, the rule is simple, right? Heat things up, they expand. Cool them down, they contract. But what if I told you that's not always true? Let's look at water's weirdest trick, one of the most bizarre and important exceptions in all of science.
So I'm asking you a direct question. Think about it. Does water always expand when you heat it? Your gut instinct probably says yes, but the real answer is, no, it doesn't. And here's the proof. Look at this graph. It shows the volume of water as you warm it up from 0 degrees Celsius. Now check this out. From 0 to 4 degrees, instead of expanding, the water actually shrinks. Its volume goes down. That means water is at its absolute densest. It's most packed together at 4 degrees Celsius. It's only after 4 degrees that it starts behaving normally and expanding as it gets hotter. This crazy behavior is called the anomalous expansion of water, and it's a huge deal.
And why is it a huge deal? Because it's literally why fish can survive the winter. Think about a lake. As the air gets cold, the surface water cools down. When it reaches 4 degrees Celsius, it becomes the densest water in the lake and sinks to the bottom. This process continues until the whole lake, top to bottom, is a stable 4 degrees. Now, when the surface gets even colder, down to 0 degrees, it freezes. And since ice is less dense than 4-degree water, it floats on top, forming a protective, insulating layer. It's like a blanket for the lake, keeping all the fish safe and sound in the 4-degree water below.
Okay, next section, a materials heat secret. Have you ever been to the beach on a hot day? The sand is like ridiculously hot. You can't even walk on it. But the water is still nice and cool. Why is that? They're both under the same sun. The answer is a special property that all materials have, kind of like a hidden superpower.
And that secret is called specific heat capacity. In simple terms, it's just a measure of how stubborn a substance is when it comes to changing temperature. Something with a low specific heat, like sand or metal, changes temperature really easily. It heats up fast and cools down fast. But something with a high specific heat, like water, is super stubborn. You have to pump a ton of heat energy into it just to raise its temperature by 1 degree.
And this brings us to probably the most important formula you'll use in this chapter. Seriously, put a big star next to this in your notes. Q equals ms delta T. Let's break that down. Q is the amount of heat transferred. M is the mass of the substance. S is that secret code we just talked about, the specific heat capacity. And delta T, that little triangle T, just means change in temperature. This formula is your key to solving a ton of problems.
Now, this idea is based on something called the principle of calorimetry. It sounds fancy, but it's just the law of conservation of energy applied to heat. It says that in a closed system, the heat lost by a hot body is equal to the heat gained by the cold body. Basically, energy doesn't just disappear. If you drop a hot piece of metal into cold water, all the heat that leaves the metal goes right into the water. None of it gets lost. Well, in a perfect system anyway.
Okay, last section, heat in daily life. We've gone through a lot of definitions and formulas, so let's wrap it all up by seeing how this stuff actually matters. Because once you get these concepts, I promise, you'll start seeing them in action everywhere.
Let's go back to water's high specific heat capacity. It really is a super substance. It's the reason we have land and sea breezes. The land heats up way faster than the water. It's used as a coolant in car engines because it can soak up massive amounts of heat without its temperature shooting up. And it's why you use a hot water bag for aches and pains. It can hold a lot of heat and then release it nice and slowly over a long time. All right, to wrap this all up, let me leave you with a final brain teaser. Imagine you have 2 cups, one made of aluminum and one made of wood. You place an identical ice cube in each. Which ice cube melts first? And more importantly, why? The answer has everything to do with what we've learned today. Think about conduction. Which material is better at pulling heat from the room and transferring it to the ice? I'll let you think on that. Thanks for joining me and good luck with your studies.